started. Okay, so so in the previous class, we were discussing about the higher order linear ODE, and what we can do is that we will continue that part and try to solve few examples, and then we move for the linear ODE with constant coefficients. So that's the plan for today's class. Okay. So let's start with a simple example. So this is the example for general solution. Example for general solution. So your question is solve the fourth order ODE. So what is the ODE? Y to the power IV minus 5 y dash plus 4 y is equal to 0. So remember, when I say IV, y to the power IV, that is nothing but fourth derivative of y. That is d4y by dx to the power 2. Okay. So we need to solve this ODE. So how to solve this one? Any method we can apply. So let's try with the method that we have is, let's take y is equal to e to the power lambda x. And ultimately we need to determine all the values like y dash, y double dash, y triple dash, and y to the power. That means y dash will be lambda e to the power lambda x, y double dash will be lambda square e to the power lambda x, y cube will be lambda cube into e to the power lambda x, and y fourth will be lambda 4 e to the power lambda x. So I can put a semicolon to differentiate them. So by putting these values in this equation, because we have y to the power iv and y double dash and y in the original problem. So putting these values in the equation, we will get the characteristic equation. Which one? I think we will get something like this: lambda to the power 4 minus 5 lambda square plus 4 is equal to 0. Okay. So now our job is to, the main task is to how to solve this particular equation. Okay. So one way is that we can think what should be a potential solution, we can apply that one. Another one is that we try to simplify this one. Like I can consider, like, let's take, let's some value mu is equal to lambda square. Okay. And then we can put this mu value in this equation, so we can rewrite this equation in terms of mu. So we can rewrite this equation as mu square minus 5 mu plus 4 is equal to 0. So if we solve this one, we will get something like mu minus 1 into mu minus 4 is equal to 0. So we can get mu is equal to 1 and mu is equal to 4. So if mu is equal to 1 and 4, then we can say lambda could be, we can change minus 1 and 1 and 4 and not 4, it should be 2. One is minus 2, minus 2 and 2. So we thought these are the roots. If these are the roots, then my solution y should be c1 e to the power minus x plus c2 e to the power x plus c3 e to the power minus 2x plus c4 e to the power 2x. Something like this we can get the solution. It's just the similar thing we did in second order, so it is just extension to that one. Okay. So this is one's general solution method, and what I will do is let's apply the similar kind of problem and try to find out a initial value problem. Address or solve one initial value problem. Right. Okay. So here is the question for you. Solve the initial value problem for a third order Euler Cauchy equation. So what is that equation? Here is the equation: x cube y triple dash minus 3 x square y dash plus 6 x y dash minus 6 y is equal to 0. Now since this order is 3, so we should have 3 initial conditions like this. What are the initial conditions? One is y1 is equal to 2, y dash 1 is equal to 1, and y double dash 1 is equal to minus 2. So these 3 are the given initial values, initial conditions. And this is the Euler-Cauchy equation we need to solve. So since this one is a Euler-Cauchy equation, we can just proceed according to the method we discussed before. What was that? To solve this, let's put y is equal to x to the power n is our solution. And then we have to follow the method how to extract the auxiliary equation from this Euler-Cauchy equation by putting these values. Right. That means what I need to determine? I need to determine y dash, that is m x to the power m minus 1. Then y double dash is equal to m into m minus 1 into x to the power m minus 2. Then y triple dash is equal to m into m minus 1 into m minus 2 x to the power m minus 3. Okay. Now let's put these values in the original problem, just like we did in the previous cases. So when we put these values in the original problem, then this particular problem we can rewrite as m into m minus 1 into m minus 2 into x to the power n minus 3 m into m minus 1 into x to the power n plus 6 m x to the power n minus 6 x to the power n is equal to 0. So taking the x to the power m common, or just divide it, we'll have a simple equation that is m into m minus 1 into m minus 2 minus 3m into m minus 1 plus 6m minus 6 is equal to 0. And solving this one, we will get m cube minus 6 m square plus 11 m minus 6 is equal to 0. So this one is my auxiliary equation. My job is to find out the root of this m. My job is to find out the root of this n, and how to do that. One of the way I can guess some root. Okay. So because if we guess you look into this equation, I can easily guess one solution, one root. Can you guess one? Yeah. Right? I can easily guess one of the root will be m is equal to 1. Easily I can guess. So, if I guess, if we guess the root m is equal to 1, okay, then by dividing m minus 1, we can get the other roots, right? So we can get the other roots, and if we do that, we will get the root is m is equal to 2 and 3. Okay, I am not going in detailed calculation. Okay. So we have 3 roots. What are those? We can just write like m1 is equal to 1, m2 is equal to 2, m3 is equal to 3 something. So we can have the solution, or the general solution we can have y is equal to c1x plus c2x square plus c3x cube. So this is my general solution. But my job is to find out the specific solution, right? Initial value, because this one is the initial value problem. Okay? So what I need to do, I just need to find out y dash, y double dash, okay? And then put the initial values in this program, in those values. So if I try to find out what is my y double, y dash, it's c1 plus 2c2x plus 3c3x square. And what is my y double dash? That is 2c2 plus 6c3x. So if you look into these problems, what are the initial values? For this one, y1 is equal to 2. For this one, y dash is equal to y dash 1 is equal to 1, and for this one y double dash 1 is equal to minus 4. So if I put this value, I can rewrite this one will be 2 is equal to C1 plus C2 plus C3. Because the x is equal to 1, y is equal to 2. And for this one, I can write 1 is equal to C1 plus 2C2 plus 3C3. And for this one, I can get minus 4 is equal to 2 C2 plus 6 C3. Right? So now my job is to solve these three equations and to determine the value of C1, C2, C3. Okay? So if I try to solve these three equations, okay, I will get some value like C1 is equal to 2, C2 is equal to 1, and C3 is equal to minus 1. So then my particular solution y is equal to 2x plus x square minus x cube. This is my particular solution. So I believe all of you got the idea how to solve the higher order ODE, right? I just gave you two examples. One is order culture with initial values, another one is the general solution. Yes, right? Okay. So if you are okay with this, let's move to a higher order homogeneous linear ODE with constant coefficients. That is, okay. So we saw very simple examples. Because if you think about the higher order linear ODE with constant coefficients, in the second order we have three cases. You remember? The independent roots, then the real double roots, then complex conjugate roots. A similar situation we could have in a higher order root. Okay. So let's discuss that one. So higher order linear ODE with constant coefficients. Let's discuss this one. So we already know the second order linear ODE. Okay. In second order, it was like y double dash plus a y dash plus dy is equal to Rx, where Rx is equal to 0 means it is homogeneous, and is not is equal to 0 means non-homogeneous. If you remember this one, right? So first our focus will be homogeneous one. Okay. After the homogeneous, we can discuss about the non-homogeneous. We can do the similar kind of thing in the nth order. So consider the similar kind of scenario for a nth order ODE. So for nth order, the ODE would be y to the power n. I am putting n in the bracket, that is defining it is derivative. Okay. yn plus a n minus 1 y n minus 1 and plus I can write a1 y dash plus a0 y is equal to so here yn is equal to dn to the power y by dx square, that is n derivative. And a n minus 1, a n minus 2 to a1, a0 are constant coefficients. Right. And to solve these ODEs, what we can do, simple method is to substitute y is equal to e to the power lambda x. Okay. Solve this ODEs, we substitute y is equal to e to the power lambda x. And we will get the characteristic equation by substituting. Okay. Now, then the characteristic equation we can get is lambda to the power n plus a n minus 1 lambda n minus 1 plus you can get something like this a1 lambda plus a0 is equal to 0. So this one is my characteristic equation. So basically, if you compare this to the second order, what exactly it means? It means if this lambda is a root of this equation. Which equation? So when I say this equation means this particular one. This particular equation. Okay. This equation. Then we can say y is equal to e to the power lambda x is the solution, is not exactly is a solution, is a solution of the ODE. So the next step is we can apply the same numeric method to identify all roots, because after identifying the roots we can find out the solution, the general solution. Okay. So we can apply numeric methods to identify all roots. Now, what are these roots? So basically, the roots we will get are, we can classify them in the following categories. First one is the distinct real roots. Okay. Second one is simple complex roots. Third, multiple roots. And fourth, multiple complex roots. So basically, if you carefully observe what was in the second order form, because we take the second order as a base to study the higher order. In the second order, we have real, no, we have distinct independent group, right? Then we have the real double root, and then the complex conjugate. So if you relate them, you can easily relate the distinct real root is quite this one. And multiple root and a real double root is this one. Right? But the complex root is actually these two. So these two are part of the complex root. Right. Now our job is to figure it out how actually they look like and how we can categorize these problems. All the higher order ODE will be classified into these four different categories. Right. So let's take one example. To understand the very first one, distinct to real root, then we'll go for the next one. Okay. So first one is the distinct real root. You look into so basically in this case, if all n roots, that means the lambda 1, lambda 2, lambda 3, up to the whatever, the lambda n, they all are different. So are real and different. That means I can say lambda 1 is not is equal to lambda 2 is not is equal to lambda 3 and not is equal to, I can say, lambda n. They are completely indifferent. In such scenario, the basis or the solution basis, n basis, we can say y1 is equal to e to the power lambda 1x, y2 will be e to the power lambda 2x, and so on to yn is equal to e to the power lambda nx. And the general solution y is equal to c1 e to the power lambda 1x plus c2 e to the power lambda 2x and so on to cn e to the power lambda nx. So this one is the basic way, the basic method to calculate the distinct real root. Okay. So let's take one example for this categories. So I am writing this equation, and your job is to find out the solution. Example of this categories. Solve the ODE. Here is the ODE, y triple dash minus 2 y double dash minus y dash plus 2y is equal to 0. Solve this ODEs and tell me the general solution. have any answer? Yeah.
Equals to C1 e to power x plus C2 e to power minus x plus C3 e to the power 2x.
This one?
2 minus
Oh, yeah. Okay. All of you getting the same answer? Okay. Okay. So now in this, when we got this kind of solutions, like y1, y2, y3. No, you guys need one extra.
The extra homework is
Yeah. You can do either, okay, maybe 4, 5 or more. 4 quiz.
Yeah.
Yeah, total will be 9, right? Okay. Maybe we can have one quiz on higher order linear OD and another quiz on Laplace that we will study next. And we can have one more homework which will be overall. Yeah, something like that. Okay. So let's finish this simple, higher order. Then we can have one quiz on higher order. And then we will continue the Laplace as well. Okay, so basically the thing is that as we know, this is this linear ODE, so we can also check the dependency of these ODEs, linear dependency. So how to do that? The same Roxian. You can apply the Roxian. So here, specifically in the Roxian, here is a little bit, one concept is there, so let me just take a few minutes to explain this one, then we'll come back to the roots we have discussed. Okay, so what was that? It's the linear independence of the solutions. So we can use the Roxian method. So basically in this case, if our n solutions are y1 is equal to e to the power lambda 1x, y2 is equal to e to the power lambda 2x, and so on to yn is equal to e to the power lambda nx. Then we calculate the Roxian. W is equal to e to the power lambda 1x, e to the power lambda 2x, and so on to e to the power lambda nx. Then lambda 1 e to the power lambda 1x, lambda 2 e to the power lambda 2x, and lambda n e to the power lambda nx. And we can proceed in that way, lambda 1 to the power n minus 1 e to the power lambda 1x, lambda 2 to the power n minus 1 e to the power lambda 2x, and so on to lambda n to the power n minus 1 e to the power lambda nx. So this we need to calculate the determinant. So taking this value, we can rewrite this one as e into 1 lambda 1 and so on to lambda 1 to the power n minus 1, then 1 lambda 2 and so on to lambda 2 n minus 1 and so on 1 lambda n and to lambda n to the power lambda n minus 1. And what is E? We can say here where E is equal to is the exponential of exp exponential of lambda 1 plus lambda 2 plus lambda n into x. Okay. So here E cannot be 0 as it is an exponential function. And W is equal to 0 if the determinant on the right is which one? So this one. I'm talking about this determinant. So W could be 0 only if this determinant will be 0. Otherwise it will be non-zero. So this determinant has a special name, and that is called Cauchy determinant. Or its name is this one. So the determinant. So basically the linear dependence or independence, we can just going to calculate the determinant. By calculating the determinant, we can decide without taking the derivative, all those things. We can just calculate this lambda values, and based on that lambda values we can decide whether this it is a linear independent, solutions are linearly independent or linearly dependent. Okay. Okay, so let's come back to the problem we were discussing. So we have 4 cases. What are those? I forgot. Distinct real root, simple complex root, multiple roots, and multiple complex roots. Okay. So we discussed about multiple distinct roots. So let's discuss about simple complex root. So basically, if complex roots occurs, they must occur in conjugate pairs. Why? Since the coefficients of the equation, which equation? The characteristic equation. Coefficients of the characteristic equation are real. You understand which equation I am talking about? Okay? Which equation I am talking about? Okay, so basically the OD, okay, so the equation that is coefficients of the, okay, let me little bit correcting this sentence. Okay, so coefficients of the OD of the given OD. Given OD are real. Okay. Now the next thing, if lambda is equal to gamma plus I omega is a simple root of the characteristic equation, then the conjugate, then lambda bar is equal to gamma minus I omega is a conjugate. Right? So in that case, the corresponding linearly independent solutions are y1 is equal to e to the power gamma x cosine omega x, and y2 is equal to e to the power gamma x sine omega x. Right? Now you can this is pretty much same as the second order complex conjugate scenario, right? Then why I am talking about it's a simple complex root? Why? So let's take one example to figure it out, because basically the scenario is that it is not just the complex root, it will come with simple root with complex root. Now what is the simple root? Just like we have the independent root we have. Okay, so maybe I will take one simple example to make you realize the scenario. Okay. So example, and I will take not just a general solution, let's also consider the initial value solution as well. Okay, so solve the initial value problem for the given OD. So what is this? Y triple dash minus Y double dash plus 100 Y dash minus 100 Y is equal to 0, and Y0 is equal to 4, Y dash 0 is equal to 11, Y double dash 0 is equal to minus 299. Right? So first, what is the characteristic equation of this OD? If you solve it just by putting y is equal to e to the power lambda x. Okay, so if we put e to the power lambda x, then we can get the characteristic equation is this one, lambda cube minus lambda square plus 100 lambda minus 100 is equal to 0. Yes. Fair enough. Now, if you carefully observe this, we can easily guess one of the root to this equation will be which one? So I can clearly mention here. By inspection we can get a root 1 and by dividing lambda minus 1 we can get the other roots. Other two roots. So what are the other two roots? If we carefully divide, we can get the other two roots are plus minus 10i. So basically the three roots we have, one root is lambda 1 is equal to 1. Other two is, we can say lambda 2 and lambda 3 is 10i and minus 10i. Okay. By considering these roots, I can now write down the solution, my general solution y is equal to c1 e to the power, look into this root. Two are complex conjugate and one is the simple one. That's why we gave the name is like, not we actually, the author of the book or maybe those who have proposed this idea. They gave the name simple complex root. So we can say it is c1 e to the power x plus a cosine 10x plus b sine 10x. Right? And since our objective is to put what? Our objective is to find out the initial values. Because this is the initial value problem. So better we should calculate y dash and y double dash. So if you calculate the y dash, it will be c1 e to the power x minus 10 should be minus 10a sine 10x plus b not exactly 10b cosine 10x, and this one will be c1 e to the power x minus 100a cosine 10x minus 100b sine 10x. And if we carefully check the initial values for these ODs, for this one, y0 is equal to 4. For this one, y dash 0 is equal to 11. For this one, y double dash 0 is equal to minus 299. So then my job is to put these values and try to find out the specific values. So if I put these values, try to determine, I can say this one will be 4 is equal to C1 plus A, and for this one it will be 11 is equal to C1 plus 10B, and for this one it is minus 299 is equal to C1 minus 100 A. So then my job is to solve these three. So solving them, we will get, by solving, we will get A is equal to 3, B is equal to 1, and C1 is equal to 1. And then the specific solution y is equal to e to the power x plus 3 cosine 10x plus sine 10x. Right? Next one, multiple real roots. So, since the concept is pretty much same to the second order and first order, so I'm not doing too many exercises, I'm just telling you the concept and try to give just one example, so you can follow it easily, right? Okay. Now, in the multiple real root, so if you remember in the second order linear OD, basically that was the case when lambda 1 is equal to lambda 2 is equal to lambda. So in that case, if we take one solution y1 is equal to e to the power lambda x, then the second solution y2 usually we got x into e to the power lambda x. and you know how to find out this x. Why we take x, y2 is equal to x e to the power lambda x, because we already discussed how to find out that one. Because you apply some technique or which one? Reduction method, right? You apply reduction method to reduce and find out this one using some arbitrary function as a solution. U into y1 is equal to y2, something like that, right? So that is how we did. So the similar way in an nth order, in a nth order ODE, the solutions are e to the power lambda x, then x into e to the power lambda x, then x square into e to the power lambda x, and so on to x to the power n minus 1 e to the power lambda x. It has to be continued like that. If there are 3 roots, then e to the power lambda x into e to the power lambda x, then x square into e to the power lambda x. That process will continue like that. Okay? Now, there might be a scenario like a solution like although we say it's the multiple double roots, maybe we can found some roots. There are multiple roots. Let's say like lambda 1 is equal to lambda 2 is equal to lambda 3. Okay, and these are the 3 roots which are equal, and another root is like lambda 4 is equal to lambda 5, something like that. There are total 5 roots of a solution, and 3 roots are equal, another 2 roots are equal, maybe another root is different. Okay, so and another root is let's say lambda 6. Suppose there are 6 roots, first 3 roots are equal, another root, next 2 roots are equal, and that was another root. Okay, so in that case, the solution would be that we can give it one name. Let's say this one is nothing but lambda 1, and these 2 are, let's say, lambda 4, and this one is the lambda 6. Right? In that case, the solution should be e to the power lambda 1x, x into e to the power lambda 1x, and x square into e to the power lambda 1x. Right? And for this 2, it is e to the power lambda 4x and x into e to the power lambda 4x. And the last one is as it is, e to the power lambda 6x. Are you getting me? Okay. So let's take one example. So if you have any doubt, it will be clarified. Okay. Example. So here is the ODE. Let's say y to the power v minus 3 y to the power iv plus 3 y triple dash minus y double dash is equal to 0. This is the ODE with 5th order ODE. So quickly we can write down the characteristic equation of this ODE. So the characteristic equation of this ODE will be lambda to the power 5 minus 3 lambda to the power 4 plus 3 lambda cube minus lambda square is equal to 0. Right. So if we solve this characteristic equation, we will get the ODE, because if you carefully see, lambda square is quite common in all cases. Okay. So we can break it and we can have the solution we can get is lambda 1 is equal to lambda 2 is equal to 0. Basically, what exactly this one is. Sorry. So if you simplify this ODE, it is nothing but lambda square into lambda minus 1 cube is equal to 0. If you solve this one, so then I can easily say lambda 3 is equal to lambda 4 is equal to lambda 5 is equal to 1. These are the 5 roots. So if these are the 5 roots, then the basis or the solutions are y1 is equal to 1, y2 is equal to x, y3 is equal to e to the power x, y4 is equal to x into e to the power x, and y5 is equal to x square e to the power x. Are you getting me? Because y1 is e to the power lambda 1 x, y2 is x into y1, y2 is x into y1, and so on. You can calculate. So then I can simply say my general solution y is equal to c1 plus c2x plus c3 plus c4x plus c5x square into e to the power x. So this one is my solution. The general solution I have. Right. Now the last part left, that is called the multiple complex roots. The previous one was simple multiple roots. Any confusion? Okay, the previous complex root was simple complex root. But here we have not just single complex root, we could have multiple complex roots. Okay. Or we can say it is a complex double root. Okay, complex double root. Okay, so here is the case. Okay. So it is the case of complex double root. What is this complex double root? So first thing we have the complex root. Lambda is equal to gamma plus I omega. And as we know, there will be not just complex, always there will be a complex conjugate. So then the conjugate root lambda bar, that is gamma minus I omega. Okay, but the point is they are complex and double. So in that case, the corresponding solutions are, what are those? For gamma, it will be e to the power gamma x for lambda case, cosine omega x, and e to the power gamma x sine omega x. This is the complex one. Complex and its conjugate. But for the double one, what will be? It will be x into e to the power gamma x cosine omega x and x into e to the power gamma x sine omega x. Understand this one. This and this. This. So this one is the first one is the complex conjugate, complex double, conjugates double. That means we just, for when we have a double, we just multiply 1x. That is the standard. So if I will explain you this one, the first two results are from e to the power lambda x and e to the power lambda bar x. Complex and conjugate. Okay. Second two results are from x into e to the power lambda x and x into e to the power lambda bar x. Right? Then the solution general solution of y is equal to e to the power gamma x a1 plus a2x cosine omega x plus b1 plus be 2x sine omega x. Carefully observe. Questions will be very tricky in this scenario. Okay. Now, in this case, if I will ask for a complex triple root, is a double root. This is the case of a double root. Now, for a complex triple roots, what will be the solution?
E to the power gamma x cosine omega x.
No, you will. I have already the double root solution. So tell me the last one.
A plus a1 plus a2x plus a3x squared.
Yeah. Basically, the solution is this one. X square e to the power gamma x cosine omega x, right? And other one will be x square e to the power gamma x sine omega x. So if it is a fourth root, then we can add another x and so on. Same is also applicable to the simple root or a double root.